Good morning, ladies and gentlemen. Now it's time to start our session 2A of this FIB PhD symposium.
So perhaps Hugo, you can start to present yourself.
Yes, well, I am Hugo Corres. I am professor at the Polytechnical University of Madrid. And I am also a designer in a FECOR company, which is an structural company.
So my name is Motohiro Ono. I'm working now as an assistant professor at the University of Tokyo, Japan. And I'm very honored to serve as a co-chair of this session. I'm very looking forward to presentations at brilliant PhD students. Now I'm working on 3D concrete printing technologies, as well as modeling and simulation of concrete structures, especially like durability issues. So yeah, that's all from me. Thank you.
Okay, and we have another co-chairman, Professor Karim Ait Mokhtar. He is not able to be with us, and so we will be only Motohiro and myself. And we have the very important assistant of Professor Farid Benjou German, who is also with us. This session is related to the durability and life assessment. We have 3 speakers today. And the first one will be Marie Sereng. She is with us, and she will make a presentation related to accelerated carbonation of recycled concrete aggregates. Marie, the floor is yours.
Thank you. Hello, everyone. I'm Marie Sereng. I'm a PhD student at the Gustave Eiffel University. My supervisors are Asad Jarbi, Otman Omikrin Metalsi, Patrick Dangla, and Jean-Michel Torrenti. I'm very glad to be here and to present you my work about the accelerated carbonation of recycled concrete aggregates. About the outlines, I will begin to present you the context and the objectives of this study. I will continue with the experimental program, especially the development of the process of accelerated carbonation. I will continue with the results, especially the parametric study of the effect which affect accelerated carbonation. And I will finish with some conclusion. About the context, as Bernard Mathieu said yesterday, the production of cement represents 5 to 7% of CO2 emission worldwide. 500 kilograms of CO2 per ton of clinker are released by decarbonation. The aim is to reduce the ecological impact of cement. RCA, which are derived from demolition of all concrete structures, are composed with a natural aggregate and a old cement paste, which is responsible of lower RCA properties, has high porosity and high water absorption coefficient. The use of recycled concrete aggregates can preserve raw materials and promote circular economy. Due to this fact, the French National FASCAR project has the main objective to uptake CO2 in recycled concrete aggregates by the reaction of carbonation. This reaction is a reaction between CO2 and cement hydrates and forms calcium carbonate, which fill recycled concrete aggregates porosity to improve RCA properties. The second aim of the National FASCAR project is to optimize the maximum of CO2 uptake in RCA in industrial application. For this, we have 3 industrial equipments which are used to determine and to verify the practical feasibility and application with high volume of RCA. The first equipment is the rotating drum at Vica in France. The second is a free-desired bed cooler at Lafarge, also in France. And the third is a static process with a continuer at Clamas, also in France. There are two main objectives in this study. The first is the carbonation of recycled concrete aggregates with the accelerated carbonation and a new calculation of CO2 uptake and a complete parametric study of all the effects that which affect accelerated carbonation. And all the results can be a database or guidelines for the industrial application. The second objective is the improvement of the RCA properties, especially the effect of carbonation on the water absorption coefficient. About the experimental program and the development of the process of accelerated carbonation, we have several steps on this process. The first step is the determination of the water content of recycled concrete aggregates. Water content is an essential parameter for carbonation. So we need to determine an optimum of water content to obtain the maximum of CO2 uptake. For that, we have a pretreatment, we have a water pretreatment. RCA are dried and RCA are immersed in water, followed by controlled drying to obtain the required water pretreatment. After this water pretreatment, RCA are kept in desiccator. A gas of 15% or 100% of CO2 concentration is injected at atmospheric pressure during 24 hours. After accelerated carbonation tests, RCA are dried to remove all free water. The CO2 uptake is evaluated by mass monitoring and by the difference between the mass if final dried and the mass initial before water pretreatment, plus a factor which is mGW. This mGW is the mass of water generated by the carbonation of Portlandite, because in our study we suppose that only Portlandite produce brown water during its carbonation, because some previous study demonstrate that the carbonation of CSH don't produce brown water during carbonation. So we know that during carbonation, 1 mole of Portlandite produces 1 mole of water. So the mass of Portlandite is determined by TGA analysis, and the factor mGW is evaluated by the mass of carbonated Portlandite and the molar ratio between CO2 and Portlandite. About the determination of recycled concrete aggregates water absorption coefficient, RCA are saturated in water by an air vacuum during 24 hours. For coarse recycled concrete aggregates, they are dried by a towel to obtain the SSD state. The SSD state is a saturated surface dried state, which is a condition where the pore of recycled concrete aggregates are filled by water, but we don't have any free water at the surface of recycled concrete aggregates. For fine recycled concrete aggregates, the SSD state is obtained by an evaporometric method. And at the end of the obtention of the SSD state, RCA are dried. And the water absorption coefficient is determined by the difference between the mass at SSD state and the mass dried. For the first effect of our result, the first effect is the effect of natural carbonation state for recycled concrete aggregate derived from demolition concrete. We have 3 recycled concrete aggregates. The first is CB14, and after phenolphthalein spray, we can observe that they are non-carbonated. The second recycled concrete aggregates are RB14C, and after phenolphthalein spray, we can observe that they are partially carbonated. And the third recycling concrete aggregates are RB14. And after phenolphthalein spray, we can observe that they are totally carbonated because of a storage of 6 years before accelerated carbonation tests. So on the graph, we can observe that CB14 has the more CO2 uptake of 50 grams per kilogram because they are not carbonated. And the lower CO2 uptake is for RB14 because they are totally carbonated with a CO2 uptake of 9 grams per kilogram. So we can say that more than they have natural carbonation, so the CO2 uptake decreases. And the second effect on this graph is the effect of water content. As I said before, at low water content, we have low CO2 uptake. The curve increases to a maximum of CO2 uptake at an optimum of water content for each RCA. And after, curve decrease at high water content to lower CO2 uptake. So it exists an optimum of water content to a maximum of CO2 uptake. The second effect is the RCA type for RCA derived from laboratory concrete. We have two RCA. The first is OC for ordinary concrete with a fraction 1/4 millimeter, and the second is HPC for high performance concrete. They have different Portlandite rate. OC have the most Portlandite rate for 4%. And a high WC ratio of 0.49. And on the graph, we can observe that OC 1/4 millimeter have the higher CO2 uptake with 22 grams per kilogram with respect to HPC 1/4 with CO2 uptake of 11 grams per kilogram. So when we have a most Portlandite rate, the CO2 uptake increases. About the effect of RCA size, also on OC and HPC RCA. For the two RCA, the fraction 1/4 millimeter have more CO2 uptake than the fraction 12-20 millimeter. For OC, for OC RCA, it's due to the Portlandite rate because the fraction 1/4 millimeter have more Portlandite rate of 4% with respect to 12-20 millimeter. But for HPC, we don't have any difference on the Portlandite rate, but we can have the hypothesis that it's CSH carbonation, but we can conclude on that because at TJ analysis, it's impossible to determine the CSH carbonation because the peak of CSH is combined to the peak of etchangite. So it's an hypothesis. About the effect of CO2 concentration for RCA derived from demolition concretes, we test two concentrations of CO2. The first is 100% of CO2 concentration to obtain the maximum of CO2 uptake for RCA. And the second is 15% of CO2 concentration because this concentration is the concentration of the gas in cement kilns. So it's the concentration chosen to industrial application. So we can observe that with the increase of CO2 concentration, CO2 uptake increases too, with a maximum of 20 grams per kilogram for 100% of CO2 concentration. And this effect is also demonstrated for RB14C because they are crushed from RB 10-20 millimeter. And the decrease of CO2 uptake between 100% of CO2 concentration and 50% of CO2 concentration are the same, around 40%, because of their similar physical-chemical properties, because RB14C are derived from RB 10-20 millimeter. And the last effect is an answer to the second objective about the effect of carbonation on recycled concrete aggregate water absorption coefficient on RB14C. With the increase of the percentage of CO2 concentration, we have an increase of the CO2 uptake around 17 grams per kilogram. And with the increase of CO2 uptake, we have a decrease of WAC, water absorption coefficient, at the maximum around 40%. So with the increase of CO2 uptake, we have the decrease of WAC. As a conclusion, we have a maximum of CO2 uptake around 50 grams per ton of RCA for CB14 due to their because they are not carbonated. The effect of RCA type demonstrates that we have 22 grams per kilogram of CO2 uptake for OC14 because they have a high Portlandite rate. The effect of RCA size demonstrates that the fraction 1,4 millimeter have more CO2 uptake than OC, the fraction 20 millimeter. The effect of CO2 concentration demonstrates an increase of CO2 uptake around 40% between 15% of CO2 concentration and 100% of CO2 concentration. And the effect of CO2 uptake on RCA water absorption coefficient demonstrate a decrease of WAC around 40% because of the filling posed by the formed calcium carbonates. My presentation is over. Thank you for your attention. And if you have any questions, I will be happy to answer them. Thank you.
Thank you, Marie. You did very well.
I'm sorry for...
No, don't worry. You did very well. So congratulations. I don't have I have one question here.
Yeah.
Very good presentation and work. This is the question I have in my chat. How did you maintain humidity in CO2 curing camber? This is the first question.
Yes, I don't maintain humidity because I impose water content before accelerated carbonation test, and I don't impose humidity with some salt in the curing chamber.
We have another question from Israel. Thank you for a very interesting presentation. The CB aggregates come from concrete beams that were 2 years old. To what extent do their results represent realistic recycled aggregates? Abby.
Oh, yes, yes. Yes, for these aggregates, we tested to be as a reference, but yes, I know that it's not represent realistic recycling aggregates. I'm okay with that, but it's more like a reference for us. It's to determine how recycled concrete aggregates can uptake CO2. But yeah, I know it's not like realistic recycled aggregates, yes, of course.
Avi, are you okay with the answer? Yes, thank you. It's the answer of Avi. So I am not expert in this field, but I had the same question. Normally, recycled aggregates have an age, and which is the influence of the age of these aggregates in this process.
Yeah.
Because I can imagine that the age of the aggregates has play a very important role.
Yeah, that I can. I said before about the RB14 because they have stalled during 6 years, so they influence the CO2 uptake. Yes, of course.
Okay, thank you. Iveta, who was the first, did the first question, has written, yes, the answer was good, but still there is some relative humidity, isn't it? Or do you have a vacuum in the chamber?
Yeah, I don't have, yes, yeah, I can read the question.
You can read the
yeah.
question.
Well, thank you. Yes, I don't have a vacuum in the chamber. I test this, I think 2 years ago, but there are no influence on the CO2 uptake. But there is some relative humidity because the aggregates are have a certain water content. So I check the relative humidity with a humidity sensor, but I don't impose humidity relative humidity to aggregates. How I can say, I prefer to be on realistic approach because sometimes we have rain, and when rain is stopped, we have drying of concrete. So we don't have relative humidity all the time. So yes, my approach is more realistic. And because on industrial application, we can apply relative humidity. So we need to impose water content, and that's all. That's it.
Okay. Can you read? We have 2 more questions.
Okay. Oh my God. Yes. Very good. What is the ambient? What was it? The ambient gas. It's azote. Azote. I don't have in English. Azote into nitrogen. Yes, nitrogen. I'm sorry. It's nitrogen for the ambient gas of TGA. Sandrine. Have you evaluated the effect of the accelerated carbonation on the absorption properties of the aggregates and its use on cricket mix? No, I don't evaluate the effect of accelerated carbonation when we use aggregate on concrete mixes, but in the national FASCA project, this effect will be studied, but not by me. Hamel Lukini, thank you for your interesting presentation. Did you characterize the porous network of different aggregates by MIP, for example? Can we find a relation of CO2 uptake with the physical properties? Yes, I characterize the porous network with MIP, but I don't do any relation at the moment between CO2 uptake and the physical properties. But in my thesis, I will do that. I think it's the last question. I don't
yes,
have
I think so.
question. Yeah.
Is there any other question? Last opportunity. Okay, if not, Marie, thank you very much. Well done.
Thank you very much.
And
thank you.
We had an interesting discussion, and we will